Hello and welcome to this lesson on estimating to check from me, Mr. McIver, here at the London Central and North West Maths Hub. Estimating can be a very handy way to check whether or not a complex calculation you've done using a calculator is reasonable. It can also be useful when someone tells you a numerical fact. A quick estimate will often help you decide whether or not the thing they're telling you is reasonable or clearly ridiculous. So we could think of a subheading for today's session as, is that number reasonable? Here's an item from the Daily Mirror in 2017. After 220,000 haircuts, this hairdresser has finally retired. Is it even possible? Let's look at some of the small print in the article. In particular, that 220,000 haircuts and 72 years. Those are the numbers we have to work with, so we can do a quick check. 220,000 haircuts a year for 72 years means that number of haircuts per year. And as there are 365 days in the year, we could say that, well, that's an average of 8.4 haircuts a day. Of course, she didn't really do 8.4 haircuts a day on average, but 8 or 9 a day seems pretty reasonable to me. But before we say this is a perfectly reasonable number, let's take a moment to think about what we've assumed to carry out these calculations. The first thing we did was do 220,000 divided by 72. Well, of course, that assumes that she worked every year and never took a break to have a family or do anything else. I suppose that's possible. But the next calculation assumes something really quite extraordinary, that she worked 7 days a week for 72 years and never took a holiday or even had a day off sick. This sounds astonishingly unlikely. Our modelling assumptions, which are really just intelligent guesses, are based on some general knowledge. Most of us have some idea of what happens in a hairdresser. They're open most days for most of the day. And we also have some knowledge about the number of days in a year. The calculation we did to figure out whether 220,000 haircuts is a reasonable figure was the number of haircuts in total divided by the number of days Kathleen worked. By assuming she worked 7 days a week for 72 years without a break, this is the maximum possible number of days she could conceivably have worked. By dividing this number of 220,000 by the maximum possible number of days, our figure of 8.4 haircuts is the lower bound for her work rate. She must have done at least 8 or 9 haircuts a day, even if she had worked every single day for 72 years. So let's look at an upper bound. First of all, let's assume she took some years off to have a family. 15 years off in total, so instead of working for 72 years, she worked for 57 out of those 72. If we do the same calculation as we did before, number of haircuts divided by number of years, we now have a figure of 3,860 haircuts a year. Now let's put in some time off. Let's assume she worked 5 days a week and got 6 weeks holiday a year. This is actually incredibly generous. It's pretty generous by modern standards, and certainly in 1945, practically no one worked those kind of hours. But we're trying to find the minimum number of days she could have worked to get the maximum number of haircuts she would have had to have done per day. That takes her working days down to 5 days a week times the 46 weeks that are left after her 6 weeks holiday. So, the number of haircuts she would have had to have done per day is 16.8 haircuts. So, we now have an upper bound for the number of haircuts per day. Our estimation has led to these figures. In order to have carried out her 220,000 haircuts, Kathleen must have carried out an average of between 8 and 17 haircuts a day. Is that reasonable? Well, you've probably formed an opinion already, but just stop and think what you needed to know to form that opinion. You need to know something about what happens in hairdressers and how long it takes to give a haircut. You also need to know a bit about how many hours people work a day. Well, if Kathleen worked an 8-hour day, that means she must have done 1 to 2 haircuts an hour. That sounds fairly reasonable. Therefore, 220,000 haircuts in a career is indeed possible. Now I'd like to look at a slightly different kind of check estimate, and this one involves a little bit more thinking to construct the model. Before railways came along in the 19th century, The only practical way of moving heavy goods around the UK was by boat. And if you weren't on the coast, that meant using rivers or canals. Now by 1800, the UK had a pretty extensive network of these inland waterways, but moving things by water has one serious problem. Water isn't very good on hills. It has a tendency to run down to the bottom. The way you get around this is by building things called locks. Here's a picture of a very large lock. The body of water at the top of the picture is at a higher level than the body of water at the bottom of the picture. But the bit in the middle, between those two sets of gates, called lock gates, can be raised or lowered. In order to move from the lower to the higher level, the lock gates at the lower end are opened, as shown in this picture here. The boat enters in through the open gates, and the gates are closed behind it. The valves allowing water in from the top level are then opened, raising the water level and the boat, which can then travel out through the higher level gates and continue on its way. A very simple system and very effective. Now let's look at one operating in real life. The narrowboat at the rear of this picture wants to move down through the lock. And so the valves have been opened here, allowing the water in the lock to rise up so that the boat can move in at the top. As you can see, the water is entering the lock very quickly. The question is, exactly how quickly? As I was travelling through this lock, somebody turned to me and said, "The water is flowing into this lock so fast, it would fill your bath 10 times a second." 10 times a second? How on earth did he work that out? Let's do a quick estimate to see if that figure is reasonable. And to do that, the first thing we need to do is come up with an estimate for the amount of water in a bath and the amount of water in a canal lock. So, here's a fairly typical bath, and here is a lock, rather like the one we just saw in the video. A lock is actually quite a boxy sort of shape, so it's reasonable to model the interior shape of it as a cuboid. A bath, well, it's got lots of rounded edges because it looks nice and it means you won't hurt yourself, but to keep life simple, we are going to model them both as cuboids. Okay, now let's add some dimensions. How big is a bath? Well, the easiest way to judge that is to think, how big is a bath compared to a person? Now, a very tall person would be 2 meters high. A useful fact to keep in mind when you're estimating is a typical interior house door is actually 2 meters high. So do you think you could fit your bathroom door into your bath? Almost certainly not. The biggest bath is going to be a bit less than 2 meters high, so I'm going to put my range of lengths as between 1.2 and 1.8 meters in length. Remember, we're talking about the interior size of the bath, not the exterior. What about the width of a bath? Well, there's the picture. Does that look half as wide as it's long? A bit less, I think. A third as wide as it's long? Maybe a bit more? Okay, let's say between a third and a half of its length. So for our bounds, we're going to take a third of the smaller length up to a half of the bigger length. So there you are, our width is between 0.4 and 0.9 meters. Finally, how deep is our bath? Now remember, we really only want to know how deep is the water you put in it. You don't normally fill baths right up to the brim. Let's have another quick look. Now, as you can see, there's an overflow drain there. I don't think it's going to be possible to fill that bath up to more than about half its width. So to get the depth of water in a full bath, I'm going to halve my estimates for the width of the bath, and those are the figures I get. To calculate the volume of water in my bath, I therefore multiply those figures together and get a lower bound of 0.1 cubic metre and an upper bound of 0.8. Quite a wide range, actually. Now let's have a look at the amount of water in the lock. Remember, I'm interested in the rate at which the water is entering the lock. I don't really need to calculate the total amount of water in the lock. I just need to calculate an estimate for the amount of water that enters in a given time period. So let's just look at the length of time it takes for the water level in the lock to increase by, say, 1 metre. That makes the sums a lot easier. What about the length and the width of our lock? Let's take another look at that video. 1, 2, 3 paces. Now a huge pace is 1 metre, so that lock cannot possibly be more than 3 metres wide. It's probably about as wide as she's tall, so let's say 2 to 3 metres. What about the length of the lock? Well, if you compare the length of the lock to its width, I think as the camera pans across, it looks like about 10 times as long, giving us a length of 20 to 30 metres. So let's go back to the model and add our new estimates. We use those figures to get a lower and upper bound for the volume of an additional metres depth of water in a lock, and we get a lower bound of 40 cubic metres and an upper bound of 90 cubic metres. So now we can try to figure out how many baths would you fill for every additional metre of depth in the lock. Well, to get the smallest possible number of baths filled, we need to take the smallest possible estimate for the lock divided by the biggest possible estimate for the bath. 40 metres cubed divided by 8 metres cubed, about 50 baths. To get the largest possible number of baths filled, we use the largest possible volume of water divided by the smallest possible bath and get 900 baths. Now this looks like a terribly wide range, and this demonstrates the difficulty we showed in the last video, which is that errors get bigger as you combine estimates. 50 to 900 baths really just tells us the answer is probably in the hundreds. Now let's try to get an estimate for how long it would take us to fill those hundreds of baths. I want to find out how long it takes the water to rise 1 metre inside the lock. So that we can judge the time, I've left a timeline showing at the bottom of the screen here. And to estimate how much 1 metre is, well, I'm going to suggest it's about halfway up that second panel on the back of the lock gates that you can see there. Right, 24 seconds. I think that's when the water starts coming into the lock. And if we fast forward, we can see that we're getting there. I think it's reaching the 1 metre point about now. Round about 1 minute. So is this figure of 10 baths filled every second reasonable? Between 50 and 900 baths can be filled by an additional metre in water depth. We figured that to fill these baths would take 60 seconds. Using our minimum number of baths, we get a minimum rate of 50 baths every 60 seconds, about 1 bath a second. Using our maximum rate, we get 900 baths divided by 60 seconds, about 15 baths per second. Our estimate, based on these modelling assumptions, is between 1 and 15 baths per second. 10 baths per second fits into this range, so it is possible. In fact, looking at the range of these figures, it looks like it's probably a bit less than 10 a second, perhaps 5, perhaps 8, but 10 is certainly possible. So that is how you can use a bit of general knowledge and simple arithmetic to check figures you have been given by other people. The process can be summarised like this. Think of a way the figure you've been given might have been calculated. That's called constructing a model. You then estimate the figures you could use to carry out this calculation. These are your modelling assumptions. You do the sum, and then, most importantly, you ask, is this answer consistent with common sense? In the first example, we got 1 to 2 haircuts an hour. Does that make sense? Yes. In the second one, we got a range of answers which included the one we had been offered. If you wanted to be more certain, you'd have to do some much more detailed measurements and calculations. That's it for this session. Please complete the tasks you have been set.